Hello class. I want to take some time in showing you the mechanism of when you take sodium metal and dissolve it in liquid ammonia, and then you treat that with an alkyne. And under those conditions, what do we get? We get a trans alkene. And then in contrast, if you take the same alkyne and treat it with different reagents, let's say Lindlar's catalyst, then you're going to get a cis alkene. And the mechanism is going to help us explain that. So I'm going to show you the mechanism of the dissolving metal reduction, and then that will help us to understand why it gives us trans alkenes. But before we jump into the mechanism, we need to understand something else about mechanism arrows. So let's just talk about something that we are familiar with. What if I take this tertiary alkyl halide and I do, let's say, start off with an SN1 type of thing here. The two electrons in this bond, when I draw an arrow like that, we see that we are going to get a tertiary carbocation because it only has 6 electrons around that carbon. But the 2 electrons all went to the bromide. So these 2 electrons right there came from that bond. And so it's the arrow that is showing you what's going on here. The arrow is saying, hey, since that's a double-headed arrow, it's saying both electrons in that bond are going to the bromine, like that. And so what we have is what's called a heterolytic cleavage. Both electrons go to the species, and so that would have to be negatively charged. But then we could have something called a radical mechanism, in which we use what's called fishhook arrows. And fishhook arrows only have one hook. You see the difference between the two? When we do this in a fishhook arrow drawn like that, what are we saying? We are saying one electron goes to the carbon and one electron goes to the bromine. And so we would have species that look like this, with an electron there, plus our bromine right here. So we would have a carbon radical and a bromine radical, because it's called a radical because we have an electron that's not paired with another electron. You can see these 6 right here are paired. It's a lone pair. This is not. It's unpaired. So whenever you have an electron or a species that has an unpaired electron, you have a radical. And so it's this fishhook arrow that you need to get used to in order to understand radical mechanisms. And radical mechanisms are when you form radicals. And so this dissolving metal reduction reactions proceeds via a radical mechanism. So we have to use these fishhook arrows. So now let's look at the reaction that we're going to talk about. Oh, I just realized I didn't tell you the name of this cleavage. This would be called a homolytic cleavage. The one above was heterolytic. This is homolytic. So when you take an alkyne and treat it with dissolved sodium metal, we have learned from general chemistry that metals want to give up their electrons so they can obtain their nearest nearest noble gas electron configuration. So it has one electron that sodium wants to get rid of. And so what it does is, notice the fishhook arrow. It's going to donate its one electron to the carbon there. And then this pi electrons in this triple bond here, we're going to break one of those sigma bonds in a homolytic fashion. We'll put one electron on this carbon and another electron on that carbon. So what we have going for us now is we have something that looks like this. We still have our double bond. And if I number these carbons, carbon 1, carbon 2, carbon 1, and carbon 2, we see that carbon 1 is going to have a p orbital with one electron in it, shown right here by that one fishhook arrow. And then on carbon 2, we'll have another p orbital, but what's happening here? This electron came and went to carbon 2, and then this one electron broke off. So now we have 2 right there. So once we get to this step, we can see that this is going to be negatively charged right here. All right, so this is going to be, put it on the carbon, I guess. So that's going to be negatively charged. Let's double check the formal charges here. 1, 2, 3, 4, 5. Yes, so that would be negatively charged. And so when we have sodium metal dissolved in liquid ammonia, our liquid ammonia is going to be our proton source. All right, it's going to act as the acid, the Lewis acid here. So this lone pair right here is going to come and grab our hydrogen atom. So that's going to give us something that looks like this. Boom. And then H right there. And then it does the same thing over again. It's going to react with another sodium metal. And we're going to see the same fishhook arrows in this step now. All right? So what's going to happen is this is still here. It's still a radical there. And so this sodium is going to donate its one electron there. And why is it going to do that? Well, it's going to give it a full-blown negative charge right here. So that's going to be negative. The carbon is going to be negatively charged. And then you can do another proton transfer with liquid ammonia. So we can see this is going to come, grab that, go like that. And then that's going to put the proton on this side, right here. And where do we want to draw that product? We're going to go down here, okay, just to draw the final product. And so you're going to see that we have, you can't see the bottom one right here, can you? So this one right here is a hydrogen right here. Let's draw the final product over here so we can see it. There we go. And that's going to be our transalkene. And that's the mechanism. But now let's figure out, using these concepts here, why does the transalkene form? Okay. Well, it all has to do with repulsion. Let's take a look at 2 scenarios, and you'll see very clearly why this reaction gives us a transalkene. So let's take a look at this intermediate first. This is after you have the alkyne, and the sodium metal donates an electron, and you get this species right here. And you can see that these orbitals right here are on opposite sides of that double bond. But what if it actually added something like this? All right, negatively charged. What about this? Why didn't it add like that? Well, because this is the low energy state and this is the high energy state. And molecules are going to take the easy way, lowest energy. So why is this the higher energy state? Well, I didn't draw it too accurately because what if those were bigger? All right. Can you now see that there's going to be some clash right there? There's going to be some electronic repulsion because we have electrons in those orbitals getting really close to each other. And so that's going to increase the energy. It's going to, in this conformation here, if the molecules could talk, they'd be like, hey, this is really uncomfortable. Why not look like this? But this is way more comfortable. And so that explains why when you are using sodium metal in liquid ammonia, you are going to get a transalkene because it proceeds via a radical mechanism, and this electronics, the electronic clashing here explains why it's going to be trans. But when you compare this to using like Lindlar's catalyst to the same alkyne, you're going to get the cis. So if we have the same alkyne and we treat it with Lindlar's catalyst, and add some hydrogen gas here, what are we going to get? We will get this as the dominant product, the cis. So what's going on here? Well, it has to do with this Lindlar's catalyst, which is what? Is it platinum or palladium? It's palladium. It's a poisoned palladium catalyst. And so you basically have chunks of metal in the reaction. The metal does not dissolve. So you'll throw it in there and you'll just see it floating around. So you have these metal chunks. And so if I take that metal chunk and just zoom in really, really close, okay? So this is the palladium metal chunk. And on its surface, the hydrogen gas or the hydrogen atoms, okay, are going to basically stick to that metal surface. And so when the alkyne comes getting close, what is it going to do? Just kind of picture it kind of like this. Let's see, boom, 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 like this. These hydrogens are just going to plop right in there from the same face. So they're adding syn. When they're adding in a syn fashion, which what I mean by that, they're coming from the same side, you will get a cis alkene. All right. Pretty slick. So our next reaction that we want to look at is hydrohalogenation of alkynes. And we've seen this type of reaction with a alkene before. We've seen that. So I'm going to pause this and clear this board. So the next reaction that we want to look at is hydrohalogenation of alkynes. But I do want to remind you that we've seen something similar when we have an alkene. When we treat that with HX, like that, what are we going to get? We are going to get the Markovnikov product, which means that the halogen is going to go to the more substituted carbon and the hydrogen is going to go to the carbon with the most hydrogens. That's what we see, and we've seen that before. But if you take a alkyne like this and treat it with equal molar amount of halogen, or the HX, sorry. So if you have 1 mole of this and 1 mole of that, okay, you're going to get a very similar Markovnikov product, but it's going to look like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. We're going to have a double bond here, And then we're going to add our halogen there, like that. But if you have excess amount of your acid, so that could be what? It could be hydrochloric acid, hydrobromic acid, right? When you have excess of this, it's going to add twice. And it's going to add both in a Markovnikov fashion and add the halogen there. So you have to pay close attention to the concentrations right here when you're dealing with an alkyne. If it's equal molar, like a 1-to-1, that only adds once, but if there's excess, it's going to add twice, like that. And what kind of halide is this going to be called? This is going to be called a geminal dialkyl halide, because we have two halogens there on the same carbon. Now, do you recall when we were doing this reaction right here, the mechanism? Do you recall that the first step in the mechanism is electron-rich pi electrons attacking the electron-poor hydrogen in this fashion. And that's going to what? Add the hydrogen there and give us a secondary carbocation, which then allows the halogen that is just broke off to come in and attack the carbocation to give us our product. Right? Remember that? Look, kind of the same, we invoke kind of the same mechanism when we're dealing with alkynes. Because what do we have here? We can have a electron-rich pi electrons come and grab this like so. And then we would have 2, 3, 4, 5, 6. And so what? We would have our double bond there. A hydrogen would have added. Now we have two hydrogens there. We already started with one. But they added there, and then what? We would have a carbocation right there. And then our halogen, whatever it may be, sees that positive charge there, comes in and attacks to give us our product. Now you do the same mechanism over again if you had excess acid. But there's a lot of controversy with this mechanism, because we know from studies a vinylic carbocation is very, very unstable. But we're invoking a vinylic carbocation here to explain this mechanism. So it's not entirely true. There's debate on how this mechanism actually proceeds. And so I don't want to get into the nitty-gritty details of this mechanism and which one's the right one, which one's the wrong one. Well, the jury's still out on that. And depending on who you talk to, they could argue their point. So what I just want you to realize is follow this mechanism the way I've shown you, but in the back of your mind, just realize, hey, that's not entirely correct, because vinylic carbocations are very unstable. Okay, so I'm not too worried about saying that this mechanism is 100% correct, because we know it's not. But we're going to use it. We're going to use it because it helps us figure out where the hydrogens are going to go. It's going to follow Markovnikov. All right? So why did this hydrogen not add at the other carbon? So let me give another hypothesis here. 1, 2, 3, 4, 5. So why did the hydrogen not add there on this first step and give us that? Well, because compare the two. This is a primary vinylic carbocation, and this is a secondary Weinlet carbocation. When you compare these two, this one is way more stable than that one. And so this helps us to understand why this reaction is adding in a Markovnikov fashion. It all has to do with that carbocation intermediate, which we know is not particularly true, but we use it to explain the regiochemistry of these reactions. Okay? So let's take a look at another radical reaction. We've seen this already with alkenes, but now we're going to apply it to alkynes as well. Recall from previous chapters that if you had a alkene and you treated it with HBr and only HBr, and we'll talk about the reasons why only HBr works in upcoming chapters, and we add a peroxide of sorts in the reaction right there. Let's make that an R. A peroxide. Remember that it's going to add anti-Markovnikov. So it's going to add the halogen there just by adding that peroxide. Pretty cool. So we can extend this idea to alkynes as well. So if we treat it with only HBr, we can't use hydroiodic acid or hydrochloric acid for reasons which we will talk about later. But what we're going to get is we're going to get a mixture. We are going to get a mixture 1, 2, 3, 4, 5, like that. We're going to get a mixture of E. So this would be E, and that would be Z, which is pretty slick. Okay, so I'm just, oh wait, what am I forgetting with the reagents here? We need our peroxide in order to do a radical mechanism. Now we will cover the radical mechanisms later on. I just want you to be aware that we've seen this before, and it does work with alkynes as well. All right. And you also see the correlation here, anti-Markovnikov. Okay. Okay, so the next reaction that we're going to talk about is the hydration of alkynes. Hydration, what's that word mean? We're adding some water. Okay. So hydration of alkynes. You can take an alkyne, you treat it with sulfuric acid and some water, and you need to add some of this mercury sulfate to get the reaction going. Now what it turns into is this molecule right there. Okay? And that molecule has a very special name, and that's called an enol. The ene is for the alkene, and then the ol is for the alcohol. So when you have a double bond right here and an alcohol directly attached, we call that an enol. But enols are not going to be isolated. What's going to happen is once the enol is formed, there's an equilibrium process which says this molecule is going to tautomerize into the keto form, which looks like this. Okay. And it's cutting off a little bit, so maybe let's shrink it down. Mm-hmm. To the keto form. So, and this is called the keto form. And we call it the keto form because what do we have? We have a ketone. So what we can say is this enol keto form is an equilibrium process. But once this reaction comes to equilibrium, almost all of the enol is going to go to the keto form. Generally speaking, we can always find exceptions, right? But generally speaking, the keto form is the more stable form and the prominent product. So what we can say is when we take an alkyne and we hydrate it with some acid and mercury sulfate, we are going to generate a ketone. So put that in your head. How do I make ketones? This reaction right here, hydration of alkynes. So I want to go through the mechanism with you to show you how this all works. Okay. So let's clean this up so we have all the space, because this mechanism, there's quite a bit of steps. So the first thing that's going to happen is we're going to have our mercury 2+ ion floating around in solution. And what that's going to do is it's going to form this the three-membered ring like we've seen before, like this. It's going to generate something that looks like this. Mercury, boom, like that. Just like that. All right. Now, what's going to happen is that we had sulfuric acid and water present. So we're going to take water, and that's going to act as our nucleophile. And so this water has options now. Is it going to attack this carbon or that carbon? Well, it's going to attack the more substituted carbon based off of the same reasons that we've seen in previous examples. This carbon mercury bond is relatively weak. And it's more weak because it's going to have a stronger partial positive over here. And this is going to be a smaller partial positive. And why is this going to have a larger partial positive? Because we have an alkyl group that can donate electron density in to stabilize that. On this side, there's no alkyl groups that can come in and stabilize it. Because what would we have if these bonds totally broke? Look at it this way. If that mercury atom, if this bond broke, we would have a carbocation there. Versus if the mercury stayed on that carbon, then we would have a primary carbocation. So when we're looking at these partial positives here, this one is a secondary carbocation, that's a primary. We know primaries don't form. So when it's in this cyclic structure right here, this one's going to have a more partial positive because it's going to be more stable due to these alkyl groups donating electron density in. And so when we have our electron-rich species right here, this is electron-rich, electron-poor, it's going to what? Gravitate towards the carbon that has the more intense partial positive. And when it does that, that bond will break like that. To give us our intermediate here, that looks like this. And I'll draw it like that. Okay. And then we still have our mercury hanging on there, just like so. That'll be our positive charge there. And then what's going to happen here? We'll do a proton transfer. We have water present, so that can act as our base. Let's use this color here. We can do a simple proton transfer. And that's going to give us mercury, our alcohol plus We just generated some hydronium from this spot, right? So when we have this species under acidic conditions, okay, it's going to react. So let's draw out that hydronium like this. And so what's going to happen, you could look at it like these electron-rich pi electrons are going to come in, all right, go like that. And it's going to add the hydrogen onto the carbon that is attached to the mercury. So if we come down here, it's going to look like this. Mercury. Right, and then we're going to have a partial charge on that carbon, the hydrogen added here. And the reason why we want the hydrogen adding on the carbon that's connected to the mercury is because we need to kick that mercury off. Okay? We need to kick that thing off. And so what's going to happen here, let's see here. What we're going to do now is, because we've generated a positive charge here, this mercury bond right here, it's going to break and give its electrons to that species. And so that's going to give us what? Like this. We don't need to draw on that hydrogen. So now what did we just generate? You see that we have now generated our enol. And so the mercury fell off, so that's going to be plus our 2 mercury right there. Okay, the mercury falls off to generate our enol. And this happens when you are under acidic conditions. The mercury is going to fall off. So now that we formed the enol, we've learned that the enols are not favored at equilibrium, that they're going to favor the keto form. So now we're going to take the enol and tautomerize it into the keto form. And I'm going to show you how to do that. Let's take a look at tautomerization of the enol under acidic conditions. That's really important to understand, is that part, because we can have tautomerization under basic conditions as well, and the mechanism is going to be a little bit different. So under acidic conditions, we're going to have, we can represent the acid as hydronium. It's not really too critical for me to know exactly which one it is. Okay. And so the first step here, we could, now, what's the best way here? I'm going to show it like this, okay? What can happen is that this alkene right here is electron rich, but it's also extra electron rich because we have these lone pairs right here that can come down, and then it can come and grab it, like so. And when you do that, you're going to get what? We're going to have a double bond. You have that. The oxygen has 3 bonds to it, so that has to be positively charged. And since these electrons came down, we have 4 bonds there. So the hydrogen that was subtracted went here. There's already 2 hydrogens here that we don't need to even show. But this hydrogen right here has now been added. So what do we have? We have a total of 3 hydrogens right there. And then we generated what? The conjugate base of our hydronium, which is just water. And then we are going to have a proton transfer step where the water is going to what? Come and deprotonate that to get rid of the positive charge. And there we have our ketone. What is this step? What was this step called? That is also a proton transfer. So tautomerization under acidic conditions is just 2 proton transfers. When you think about it, based off of those 10 mechanistic steps that I've been teaching you, it's really not that hard, right? It's just a simple proton transfer. 2 of them, just in a row, to get you your ketone. Okay? Now you have to understand, though, that this is at equilibrium. And so technically we should have some equilibrium arrows here, because we can, in fact, go from the keto or the ketone all the way back to the enol. So mechanistically, how do you do that? Well, you do the exact opposite of what I just did in the green arrows. Do the exact opposite to go backwards. And that is a very good exercise to do, because you need to know this in the forward direction and in the reverse direction. So I'm just going to show it to you in the forward direction, and good exercise. Try it in the reverse direction, okay? Let's see what else needs to be said. Now let's take a look at adding some water across a triple bond, but do it in a anti-Markovnikov way. All right. So in this reaction, hydration of alkynes, what did we do? We had, let's draw it like this. We had an alkyne. We treated it with sulfuric acid, some water, and some mercury sulfate, right? And where did the water go? Or where did the, let's say the alcohol, let's do it that way. Where did the alcohol go? Carbon 1 or carbon 2? It went to carbon 2, because it was, and so it formed this guy, all right? The water molecule went to the more substituted carbon. All right? And the reasons why we explained that was due to the 3-membered ring with the mercury, right? Okay. But now we can take that same exact molecule and add the alcohol on the other carbon. What if we wanted it to add there? Do you see the difference between the two? Both are enols. It's just, where did the hydroxyl get added? The more substituted carbon or the less substituted carbon? And so that's the next reaction that we're going to look at. And it's called hydroboration oxidation of alkynes. Now, if we take the same alkyne as we've been working with, and then treat it with borane and THF, and then do a second step, the oxidation step. So step 1 is the hydroboration. Step 2 is the oxidation. And the product that we're going to get would be an enol, but now you see that the hydroxyl is added in a anti-Markovnikov fashion. But that is an enol, and so it is going to tautomerize into a different product here. And so what is it going to tautomerize into? Well, that really. I could draw in a hydrogen if I want. We've went to the aldehyde, but we still call this the keto form. This is the enol, this is the keto form, but what functional group did we make? Well, we made a aldehyde. Okay. Let's see here. Now, when you do this reaction, you can use borane, okay? But you can also replace the borane with this dicyamylborane, or you could replace the borane with the 9BBN. You don't need to remember the structures of these guys. All you have to understand and remember is that this species right here looks different. You can see an image of it in your textbook, but all you have to do is say, hey, that's going to behave the same thing, behave as the same way as borane. And same thing for 9BBN. That's basically going to behave like borane. Okay. Now, why do people want to use 9BBN over borane sometimes? Well, it's really, really big, so it's really bulky. And so 9BBN is really, really going to favor the anti-Markovnikov product. And so sometimes you just want to force it, like all the way, no chances of any side reactions. But for our purposes of our class, all three can work. All three are fine. Okay. But now that we have this enol, we need to show you how to tautomerize it to the keto form. And we have to show you how to do it under what? Basic conditions. So it's different than tautomerization under acidic conditions. So you have to make sure when you have to do a tautomerization, you take a look at what are the reaction, what's the reaction under, or what are the reaction conditions. And if you see acid, then you tautomerize based off of acid. And if it's under basic conditions, you use the basic mechanism. Okay. So what we have here now, I'm going to extend out that hydrogen because that's important in the first part of the mechanism. So the first part of the mechanism is that you are adding base. You're under basic conditions. So under basic conditions, you have to do a proton transfer. And so when you look at this molecule, you're like, okay, base, so there has to be an acid over here somewhere. What's the most acidic proton? Well, an alkyne hydrogen, or alkene hydrogen is what? Has a pKa of around 43, but an alcohol hydrogen has a pKa of around 16. So that's the one that it's going to go for. And so it does that. Why is that so significant? Well, now we have a negatively charged, and now we generated what? The conjugate acid, which is water. So now we have this charged species now that can bring a lone pair down and collapse down. And so that means this double bond has to break, and it's going to come and grab another proton. Now, where's the hydrogen going to go? Well, it's going to go to the carbon that's attached to the R group. So we have a double bond like, no, like this. And we still have that hydrogen there. We can draw that in if we'd like. Okay, and then what did we do? We added, there's already hydrogen there, so that one's that one. But then this hydrogen right there, I'm going to now add it. And there we go. And so there's our aldehyde. So hydroboration oxidation of alkynes can give us a aldehyde. But remember our starting material. Very, very important to see this. What type of alkyne was it? That was a terminal. So a terminal alkyne is going to generate a aldehyde under these reaction conditions. Well, with the time that's remaining, I think it'd be a good idea to call it a day for this content. and then we will pick up the remainder of the reactions that we need to learn in the next video. Okay? As always, reach out if you need anything.